new topic. We'll start our topic by multiplicative function. Actually, a multiplicative function is an arithmetic function. In most of the case and most of the books, arithmetic function is also known as number theoretic function. What was number theoretic function or arithmetic function? Any function is known as arithmetic function if their domain is natural numbers. Here we have to define the multiplicative function. A number theoretic function f is said to be multiplicative if f of mn equals to f of m dot f of n. So if we take another example, whatever we take during our understanding of arithmetic function, one is natural. If there is a function from natural to complex, we can take this as an example. Then suppose we can also say for an example that f of 1 equals to 1. This is a number theoretic function. So if we take another example, say m equals to, suppose as per multiplicative function definition, that f of mn equals to f of m dot f of n. So if we have that m equals to 1 and n equals to 1, then what can we say? How can we justify that f of mn equals to f of n dot f of n? Then that what will be our tau of mn? What will be our f of mn? F of 1 cross 1 equals to f of 1, which also can write in 1 into f of 1. That 1 is our f of suppose f of 1 cross f of 1, which is f of m into f of n, which is our multiplicative function. This is our defined multiplicative function. So please look, if we look into our next slide, there is a theorem that the function tau and sigma. What was tau? Tau was the number of positive divisors of an integer n, and sigma was the sum of the positive divisors of the integer n. So in this theorem they asked the statement, the function tau and sigma are both multiplicative function. We have to prove that sigma and tau both are multiplicative function. Initially we proved that tau as a multiplicative function. That means we have to show that tau of mn equals to tau of m into tau of n. They have another thing, that if tau of mn equals to tau of n, must be that their GCD of m and n equals to 1, and m and n are obviously co-primes. So we have to followed by various cases. Initially there are 4 cases as well, that in our case 1 we took m equals to 1 and n equals to 1. So in every cases, what will be the tau of mn equals to tau of 1? That is easily we can show that tau of m equals to tau of n. Similarly for m equals to 1 n not equals to 1, similarly we have that we can show that tau of m and the product of tau of mn equals to tau of m dot tau of n. And similarly, as like case 2, we also can show case 3. Both are quite similar to each other, and our main part starts from the case 4. We can take that m and n both are greater than 1. That means m and n must have their prime factorization. If the m and n both have prime factorization, we in our early lecture we know that how can express m and n as their prime factorization. These are the prime factorization of m and n. So we already have the product of m, we have mn, and since our GCD is mn, which is 1, then the product of mn will be this one. The tau of mn, obviously we know that tau of something n must be if n has prime factorization of p raised to k1 dot p raised to k2 dot pn kn, then what can we write? K1 plus 1 dot k2 plus 1 consecutive kn plus 1. So similarly, we can write k1 plus 1, k2 plus 1, kr plus 1. Similarly, in this case also we can write j1 plus 1, j2 plus 1, js plus 1, that so that this is our tau m and this is our tau n. So we can easily prove that tau n, tau of mn equals to tau of n into tau of n. So tau is also a multiplicative function. So in our next proof to prove that sigma is a multiplicative function, we can easily do our case 1, case 2 and case 3. I am focusing on case 4 only. That if we assume that if we assume that m and n both are greater than 1, that obviously m has prime factorization and n itself has prime factorization, as both are integers, then sigma of mn equals to sigma of p1 a1 p2, their prime factorization, and q also have their prime factorization. We know that sigma of n equals to p1 k1 plus 1 minus 1 by p1 minus 1 followed by pr kr plus 1 by that's the or problem sigma of n value. Here we have that what this is nothing but our sigma n, sigma m, and this is nothing but our sigma n. So we can easily say that sigma is a multiplicative function. So we have a result which says that if d is a divisor of n, d is a divisor of n, and n by d is, we have to show that n by d is also a divisor of n. So we have in our statement that d is a divisor of n. That means d divides n. So by our first theorem, whatever we did in our lecture 1, we can write it in the form of n equals to kd, because by the definition of divisibility, we all know that if there a divides b, then there exists an m belongs to and positive integers where exist a equals to bm. We already know by the definition of divisibility. So using the definition of divisibility, we can write this in the form of n equals to kd, and we can replace k as n by d, because n by d is also an integer. N equals to n by d into d. So this means it implies that n by d divides n. That means n by d is a divisor of n. So in our next proof, that show that summation d divides n 1 by d equal to sigma n by n. So what was the sigma n? Sigma n is the sum of our positive divisors, and n is our integer itself. So if we already have that sigma of n equals to summation d. So if we implies that if d is there, then we can also replace d with n by d. Then if we removes d from n from outside, then there is also only exists that summation d divides n 1 by d, which is our nothing but our sigma n by n. So we have a lemma. In our lemma, it says that GCD of mn equals to 1. Wherever we have that GCD of mn, it says that both mn and n are co-primes to each other. Then or co-prime or relatively prime. Wherever we have that GCD of mn equals to 1, then it will be relatively primes. Then the set of positive divisors of mn. We already know at our fundamental theorem of arithmetic and divisibility what is divisors and what are the divisors and what are the prime factorization. We already know about that. And that what is our statement? Mn consists of all products d1 comma d2, where d1 divides m and d2 divides n, and GCD of d1 d2 equals to 1. Furthermore, this product are distinct. So you have to prove. So initially we can take that there is a m greater than 1 and n also greater than 1. Then there exists a prime factorization of m and n. We wrote here the prime factorization of m and n, and we have the GCD of mn equals to 1. So there must not be any pi equals to pg, must not be there, there not be any pi equals to qg, where if we find the product of m cross n, we have this, and we can write d, where d is the divisors, the product. We can, if we represent mn equals to d, then easily we can write it this in the form of this. Then d, we can also define this as d equals to d1 dot d2, where d equals to d1 d1 dot d2, d1 equal to this and d2 equals to this if we represent this way. So d1 equals to our p1a1 p2a2 dot prar, which also divides by m and which is divides by n. So here is our proof, which says that there exists an m and n where d1 divides m and d2 divides n, and GCD of both d1 and d2 are 1, because this happens. So in our next theorem, it says if f is a multiplicative function, if any function is multiplicative, we already know that when a function be a multiplicative, for a function to become a multiplicative, the function must be an arithmetic function or number theoretic function. What was arithmetic function? In our arithmetic function, that our domain are always of natural numbers. So if f is a multiplicative function, if f is a multiplicative function, then it must satisfy f of mn equals to f of m dot f of n. So we have f is a multiplicative function, and f is defined by f of n equals to summation d divides n f of d. Then f is also multiplicative. We have to show that f is also our a multiplicative function. We know that f of mn equals to f of d summation. Then there is a, we can define this. If d divides mn, then we can broke our divisors d as a form of d1 and product of d2. Then we also can say that d divides m and d2 divides n. So we broke down this into this. Then we get that f of d, as we have that d equals to product of d1 dot d2. Then we broke into this f of d1 and f d2 by multiplicative function. We already know that we can write the functions as f of d1 and f of d2. Then this arises that summation f of d1 dot f of d2 equals to f of m into f of n, which is our proof. So in our next statement, it is given that to define that using earlier theorem, whatever did, or earlier that last theorem, whatever we did, that tau is a multiplicative function and sigma is a multiplicative function. So what did we know about Bardhan multiplicative function? A multiplicative function is also a arithmetic function. An arithmetic function is also known as number theoretic function. What is defined by arithmetic function? There must be the domain natural numbers. And what we know about the multiplicative function, that multiplicative function always satisfies the property f of mn equals to f of m dot f of n. Then we have to prove that tau function is a multiplicative function. To prove that tau function is always multiplicative function, we can assume that a function f of n equals to 1. There is a hint we did in earlierly that f of n can be written in summation d divides n 1. So this is a hint only. By this we can easily think that f of n equals to 1. Then we can write this in the form of 1 equals to n0, always a multiplicative function. Then the function f of n we have summation d divides n f of n f of d equals to 1. So which is our tau function. Then with there only we can say that tau of n is a multiplicative function. So if we move to our second proof, which is sigma of n is multiplicative function, again we have to show that sigma of n is a multiplicative function. Then we know that sigma of n is the sum of the positive divisors of the integer n. Then we already know by our earlier first lecture that sigma of n can be wrote in the form of summation representation divided d divides d, in the form of n. So we will take that our function f of n equals to n, always be a multiplicative function. So n can be replaced by summation d divides n any function or f of d. So it can be written in the form of summation d divides n 1, which is nothing but our sigma n. Therefore we can easily say that sigma of n is a multiplicative function. So in our current lecture we will discuss about the multiplicative function and various proofs of multiplicative function, and we relate sigma and tau, and we define the sigma is multiplicative function and tau are multiplicative function, and we found that both sigma and tau are multiplicative functions. So in our upcoming lectures, which will be lecture 3, we'll discuss about the multiplicative function more defined, and how they satisfies the various theorems in our upcoming series. And we'll also study about perfect square, square free number and all. Thank you for the watching.